this lecture, I'm going to be talking about a different way to think about black holes. We sort of, in the last section, talked about it from the perspective of a view of gravity as a force. It's something that fits very well with the kinds of physics that you studied in physics class. It's what we would call a Newtonian view. And in fact, somebody in the years right after Isaac Newton said you could calculate a point where the escape velocity from some object would be equal to the speed of light. So the concept of a black hole has actually been around for a very long time. But in this lecture, I'm going to go into some more modern stuff. And this is kind of weird to think about. In fact, it usually gives me a headache to really think about what's going on in this case. This is a kind of challenging thing to understand and really think about. Because in this lecture, I'm going to talk about black holes from the point of view of Einstein's theory of relativity. Now, Einstein has two theories of relativity. There's one called the special theory and one called the general theory. The special theory has to do with when things are traveling close to the speed of light. The general theory of relativity is Einstein's explanation of gravity. He says Newton didn't quite get it right. I mean, Newton's law of gravity works, no question about it. But he says, really, if you want to understand how gravity does its thing, what really is gravity? Thinking of it as a force is not quite the best way to think about it. In the theory of relativity, Einstein says that gravity is a curvature in space-time. Now, space-time is not something we're used to thinking about a lot. You hear it, of course, but at least you can think about time. Or sorry, excuse me, about space. Now, when I say space, I'm not thinking about like outer space. I'm talking about the mathematical concept of space, that there are three dimensions and there are locations in those three dimensions. You can imagine it as a big giant coordinate system or something like that, that it's geometric space. And Einstein had already demonstrated that time is really just another part of space, and that time can be thought of in exactly the same way space is, as just another dimension in geometry. So that's where space-time comes from. Now, the weird thing here is that we're going to talk about space being curved. If you ever read the book A Wrinkle in Time, that was getting across, that very title was getting across the idea of a curvature in space and time. And if you read that, you may remember a story that one of the supernatural characters said, okay, imagine that there's a small ant and it wants to travel across my skirt. And she holds out her skirt and the ant walks all the way across it. And she says, but what if I wrinkled my skirt? And she brought the two ends of her skirt close together, and the ant was able to just basically go from one side of the skirt to another side in a minute, because she had caused a wrinkle or a curve in the space that was represented by her skirt. Now, that's sort of an analogy to what's going on in Einstein's theory of gravity. One way you can get your head around this is to imagine a giant trampoline. Think of a big giant trampoline. And imagine that for some crazy reason, somebody has drawn a coordinate system on it, like X's and Y's. It's like graph paper. The trampoline surface is graph paper. And that's kind of what you're seeing in this picture, is the graph paper that's drawn on the trampoline. Well, now imagine that you take a bowling ball and you drop it in the middle of the trampoline. You can certainly imagine that the trampoline is going to dent around the bowling ball. And that's going to mess up your coordinate system. Your coordinate system is now going to become curved. And the distances between the lines are going to become greater or lesser depending on where you are. It's going to change that coordinate system. Einstein says that this is what mass does to space and time, is it creates this warping. This is the concept of warp drive in Star Trek, anything that you hear like that, hyperspace in Star Wars, they're all thinking this kind of thing. We're going to take space and we're going to warp it. The more mass something has, the more it warps the space. Just like with my bowling ball on the trampoline, if I, instead of a bowling ball, I had an elephant, the elephant would cause a gigantic bend in the trampoline, even more than the bowling ball would. So um, the more mass something has, the more it bends space-time. And by the way, you have mass, you are bending space and time around your body. It's just not noticeable because you don't have very much mass. But a black hole has a huge amount of mass in a very, very small space. And in fact, so much so that we would say a black hole is an infinite curvature of space and time. So what does this have to do with our traditional sort of view? Well, this is a picture from your book, and you can look at your book and sort of find this same kind of concept if you want to be able to read better what the captions say. But what we've got here, again, imagine this is my trampoline. So now, if the trampoline is flat, a straight line is a straight line. I can just draw a straight line across there. It's kind of hard to do with my little pen here, but I can draw a straight line across there from end to end. But now I put the bowling ball in. And now if I want to try to go in one side and come out the other, I have to travel a much bigger distance, and I have to manage to go down here and then come out the other side. But you could do that, like if you were a little ant trying to crawl across this, you would have to go way down into the hole and then come out the other side. So what's a black hole? Well, a black hole is a place that's so big that when you go in, it's not possible to climb back out because it is infinitely curved. It goes down forever. Now, that's not too hard to think of in this picture, although you say, what is it curved into? Well, here it's curved into the third dimension. It's curved into depth. But then you start saying, but isn't space three-dimensional? Well, what is space curved into in that case? A fourth dimension? Well, okay, fourth dimension is time. Well, what is space and time curved into? If you don't have a headache thinking about that, you're not thinking about it hard enough. It's very, very hard to envision this. You can pretty much only envision this by analogy because the curvature of space is just something that our brains are not really equipped to handle. Nonetheless, this is a theory that has been tested over and over and over. And it has been shown to be correct. And in fact, it provides explanations of some things that we see in space that could not be explained in any other way. So this is something that really is a correct way of understanding gravity. It's a warp in space-time. And a black hole is an infinite warp in space-time. So once you go into it, you can't climb back out the other side. And the event horizon would just be that distance from which you can't recover. So you're down in the hole and you can't get back out. It's much harder to calculate in this case, but there is a calculation that you can do and figure out what the event horizon is in this view. It's just very, very, very hard math. It's math that's so hard that even math majors don't do it. The only people who do it are physicists and astronomers. It's really hard. So this is just another way to think of black holes, is this infinite curving, this infinite warp in space and time.